When someone says they are using generative AI, what exactly are they using? Are they using an AI model, a capability of that model, an application such as a writing assistant, or an entire system built around artificial intelligence? These terms are often used interchangeably, but they describe different things. Understanding the distinction is an important starting point for understanding generative AI. Generative AI is a branch of artificial intelligence that can create or transform content in response to a prompt or some other form of input. That content can take many forms. It may be text, software code, images, speech, music, audio, video, designs, simulations, synthetic data, or even candidate molecular and protein structures. The word generative refers to this ability to generate a new output. But generative AI does not begin with the application that we see on our screen. Behind most modern generative AI systems lies a trained computational model. And increasingly that model is a foundation model. Foundation models are trained on broad collections of data and are designed to support many different tasks. A large language model, for example, may be able to write, summarize, translate, answer questions, analyze documents, generate software code, and conduct a conversation. Other foundation models may work with images, audio, video, or several types of information at the same time. This leads to an important distinction. A foundation model describes the breadth, scale, and reusability of a model across different tasks. A generative model describes a model's ability to learn patterns from data and use those learned patterns to produce new outputs. The two terms are therefore related, but they are not synonyms. A modern large language model can be both a foundation model and a generative model. Now consider how this differs from earlier forms of artificial intelligence. Traditional AI systems have commonly been designed to analyze information, classify observations, detect patterns, make predictions, or recommend decisions. A system may classify an email as spam. It may predict whether a customer is likely to leave a service. It may detect a fraudulent transaction, forecast product demand, recognize an object in a photograph, or recommend a film. These systems are generally answering questions such as, what category does this belong to? What is likely to happen next? Is something unusual? Which option should be recommended? Generative AI goes further. It uses learned patterns to construct a new output. A predictive system might identify which customers are most likely to respond to a marketing campaign. A generative system might then write a personalized message for each of those customers. A conventional computer vision system might identify the objects appearing in a photograph. A generative system might create an entirely new image from a written description. A code analysis system might identify a software defect. A generative coding system might propose the corrected code. The distinction is not absolute. Generative systems themselves also depend on prediction. A large language model, for example, generates language by repeatedly estimating possible next tokens as it constructs its response. The key difference lies in the purpose and the final output. Prediction becomes part of a process that produces something new. There is another distinction that is equally important, that we need to separate the generative model, the generative capability, and the generative AI application. Think of these as different layers. First comes the generative model. This is the trained computational system. It has learned patterns and relationships from data and can use those learned representations to produce outputs. The model provides the underlying intelligence. Second comes the generative capability. A capability describes what that intelligence can do. Writing text is a capability. Summarizing a document is a capability. Translation is a capability. Generating software code, creating an image, synthesizing speech, producing video, answering questions, and extracting information are all capabilities. One model can possess many capabilities at the same time. A simple analogy is the smartphone. The smartphone is the technology. Taking a photograph is one of its capabilities. The camera application is the system through which you use that capability. The same distinction can be applied to generative AI. The generative model is the technology. Text summarization is a capability. An enterprise document summary assistant is an application that puts that capability to work. And this brings us to the third layer, the generative AI application. The application is the user-facing or organizational system designed around one or more model capabilities. An application ordinarily contains much more than the model itself. It may combine the model with a user interface, prompts and instructions, organizational data, retrieval systems, security and access controls, guardrails, testing and evaluation, and human oversight. Consider a customer service assistant. The underlying technology might be a large language foundation model. Its capabilities could include language understanding, question answering, summarization, and text generation. But the application becomes useful to the business only when those capabilities are connected to company product information, customer records, policies, security systems, and the customer service workflow. The outcome might be faster and more personalized support. Now consider a research assistant. The model might be a multimodal foundation model. Its capabilities might include reading documents, extracting information, comparing evidence, summarizing findings, and generating text. The application could connect those capabilities to an approved collection of scientific literature through a retrieval system. The professional outcome could be faster literature synthesis and preparation of research drafts, with expert verification still retained. This gives us a useful chain for understanding generative AI, generative model, generative capability, generative AI application, human or organizational outcome. We can make the chain even more complete. Training data is used to develop the model. The model provides generative capabilities. Those capabilities can be adapted through prompts, retrieval, fine-tuning, data, guardrails, interfaces, and evaluation. These components are assembled into a generative AI application, and the application is used to produce an outcome: improved productivity, better communication, decision support, creative output, a business service, or some other form of value. This distinction matters because a foundation model is not by itself a customer service system, a research assistant, a writing application, or an enterprise knowledge platform. The model provides or enables the capability. The application puts that capability to work. So the simplest way to remember the relationship is this: a generative model provides intelligence. Generative capabilities describe what that intelligence can do. Generative AI applications apply those capabilities to useful tasks. And once we understand what the components are, the next question becomes much easier to ask. How does generative AI actually work? That is what we will examine in the next section. In the previous section, we distinguished between a generative model, the capabilities that model provides, and the generative AI application through which those capabilities are put to work. But this raises a more fundamental question. How does generative AI actually create something new? When you type a question into a generative AI application and receive an answer within seconds, it can seem almost instantaneous. Behind that apparently simple interaction, however, lies a much longer process. At a broad level, we can understand generative AI through 5 stages: training data, learning patterns, receiving an input, generating an output, and evaluation and improvement. Let us look at each of these in turn. The first stage is training data. Before a generative model can produce useful outputs, it has to learn from very large collections of information. Depending on the type of model, this information may include books, articles, websites, images, software code, audio recordings, videos, scientific information, business documents, or structured databases. Some of this information may be labeled, much of it may not be. Modern machine learning techniques allow models to learn from enormous quantities of material without requiring a human being to manually label every individual example. But exposure to data is only the beginning. The second stage is learning patterns and representations. During training, the model identifies statistical patterns, structures, associations, and relationships within the information it processes. A language model may learn patterns associated with grammar, vocabulary, writing styles, document structures, coding conventions, and relationships between words and concepts. An image model may learn patterns involving shapes, textures, colors, lighting, object relationships, and spatial composition. These learned relationships are represented mathematically within the model through very large numbers of parameters. This is an important point. A generative model should not normally be imagined as a giant conventional database containing a complete stored copy of every book, article, image, or web page on which it was trained. Instead, training changes the model's internal numerical parameters so that they represent patterns learned across the training material. The model uses those learned patterns when it encounters something new. This brings us to the third stage, receiving a prompt or input. A user provides some form of instruction to the system. That input may be a written question. It may be a request to summarize a document, generate an image, explain a piece of software code, translate a paragraph, analyze a chart, or create a presentation outline. Increasingly, the input does not have to consist only of text. It may include an image, a document, a voice recording, a video, software code, or several types of information combined. The prompt tells the system what the user wants, and the quality of that instruction can have a substantial influence on the result. This is why prompt design matters. A vague instruction leaves the model with considerable freedom to interpret what is required. A clearer instruction can specify the objective, audience, context, constraints, desired structure, or form of output. The fourth stage is generation. The model now produces an output based on several interacting sources of information. These include the user's prompt, patterns learned during training, information supplied within the current context, model settings, and any external information that the surrounding application makes available. For a language model, generation commonly takes place one token at a time. The model considers the text that has already been provided or generated and estimates possible next tokens. It selects a token, adds it to the sequence, and then repeats the process again and again. The response is therefore constructed progressively as generation proceeds. This is very different from retrieving a fixed, pre-written answer from a database. The system is generating a response using learned statistical relationships. Consider a simple example. Suppose you ask a language model to write a short description of a rainforest. The model does not normally search inside itself for a stored paragraph labeled rainforest description. Instead, it uses the patterns it has learned about language, rainforests, descriptions, sentence structure, and the information contained in your prompt to construct a new response. Different forms of generative AI perform generation differently. An image generation system based on a diffusion model, for example, may begin with what appears to be random noise. It then progressively transforms that noise step by step toward an image that corresponds to the written prompt. The mechanism is different from language generation, but the underlying principle is similar. The model uses patterns learned during training to construct a new output in response to an input. The fifth stage is evaluation and improvement. Generating an output does not necessarily mean that the output is good. Developers and users may evaluate it for accuracy, relevance, coherence, usefulness, quality, diversity, speed, safety, and bias. The system can then be improved in different ways. Prompts can be refined, models may be fine-tuned for particular tasks or domains, human feedback may be incorporated. External retrieval systems can provide additional information. Guardrails can constrain unwanted behavior, and domain knowledge can be added around the model. So generative AI is better understood as a continuing cycle rather than as a one-time act of generation. Train, generate, evaluate, improve, and generate again. But there is another important point. Not every generative system works in the same way. Generative AI is not based on a single model architecture. Different architectures have evolved for different forms of information and different types of generation. One of the most important is the transformer. Transformers underpin most modern large language models. They use a mechanism known as attention to identify relationships and context across sequences of information. This architecture has become particularly important for text generation, software code generation, translation, summarization, question answering, document analysis, and conversational systems. Transformers helped make it possible for models to process very large quantities of language and generate increasingly coherent and context-sensitive responses. A second important family is the diffusion model. Diffusion models are widely associated with image generation and are increasingly being applied to audio and video. During training, noise is progressively introduced into examples, and the model learns how to reverse that process. During generation, the system can begin with noise and gradually transform it into an output corresponding to the user's prompt. This approach has become particularly effective in producing detailed visual content. Another architecture is the Generative Adversarial Network, or GAN. A GAN contains two competing neural networks. One network, the generator, creates content. The other, the discriminator, tries to distinguish generated content from real examples. Through this competition, the generator progressively improves its ability to create realistic outputs. GANs have been used for image generation, synthetic media, data augmentation, and other forms of content creation. There are also variational autoencoders, usually called VAEs. These models learn compressed representations of data and can then use those representations to create new variations. They have applications in areas such as control generation, image reconstruction, anomaly detection, and exploring variations within a learned data space. And finally, there are encoder-decoder systems. An encoder converts an input into an internal representation. A decoder then uses that representation to produce an output. This approach has been widely used for tasks such as translation, summarization, image captioning, speech processing, and conversion from one type of content into another. Modern systems often combine ideas from several architectural approaches. So there is no single mechanism called generative AI operating behind every application. The architecture depends partly on the form of information being processed and the type of output required. But across these different architectures, a common idea remains. A model is trained on information. It learns patterns and representations. It receives a new input. It uses what it has learned to construct an output. And that output can then be evaluated and improved. This helps explain why generative AI is capable of producing such a wide variety of results. But just how wide is that range? Text and software code are only part of the story. Generative systems can now work across images, speech, audio, video, designs, synthetic data, and increasingly several types of information within the same interaction. And that brings us to the next section. What can generative AI actually produce? And what happens when these different capabilities come together in multimodal systems? In the previous section, we saw how generative AI learns patterns from data and uses those patterns to construct new outputs. But what exactly can those outputs be? The answer is much broader than text. Generative AI can now produce or transform many different forms of information, including written language, software code, images, speech, music, video, designs, synthetic data, and even candidate scientific structures. And increasingly, these different forms of information are beginning to come together within the same AI system. Let us begin with the form of generative AI that most people encounter first: text. Generative AI can create emails, reports, articles, summaries, proposals, scripts, marketing material, product descriptions, educational content, creative writing, research drafts, and answers to questions. But generation is only part of the capability. An existing piece of text can also be transformed. A model can rewrite it, translate it, shorten it, expand it, classify it, or restructure it. Consider a long technical report. A generative system might summarize it for a senior executive. It might then rewrite the same material for a general audience. It could translate the summary into another language, extract key points, or reorganize the contents into a presentation outline. The information begins in one form, but the model can transform it for different purposes. A second major area is software code. Generative AI can write code, complete unfinished code fragments, explain existing code, translate between programming languages, identify possible defects, generate test cases, prepare documentation, and support the modernization of older software. This makes generative AI potentially useful across many stages of software development, but there is an important qualification. Generated code is still code. It can contain errors, security weaknesses, inappropriate assumptions, or solutions that work in one situation but fail in another. So the output still requires review, testing, security assessment, and validation by qualified developers. Generative capability can accelerate software development. It does not remove professional responsibility for the software that is ultimately deployed. A third major area is images and design. Image generation systems can create illustrations, photorealistic scenes, artwork, product concepts, advertising visuals, characters, avatars, diagrams, design variations, and three-dimensional assets. They can also work with images that already exist. An image may be edited, extended, restyled, or enhanced. This changes the role of the user. Instead of beginning with a blank screen and manually constructing every visual element, a designer can begin with an idea, describe the required result, generate alternatives, and then select, refine, or modify them. The generative system becomes part of an iterative design process. The same principle extends into audio, speech, and music. Generative systems can produce synthetic speech, voiceovers, music, sound effects, audio translations, dubbing, and conversational voices. These capabilities have practical uses in education, entertainment, accessibility, media production, and customer service. A training course can be given a voiceover, a piece of content can be dubbed into another language. Written material can be converted into spoken audio. A customer service application can interact through a synthetic conversational voice. But these capabilities also introduce new risks. A system capable of generating realistic speech may also be used to imitate a person's voice. So the same capability that enables useful applications in accessibility or media production also raises questions about impersonation, authentication, and cloned voices. Generative AI is also moving rapidly into video and animation. Systems can create or modify video clips, animations, special effects, virtual environments, training simulations, marketing videos, and educational demonstrations. Video generation is more computationally demanding than generating a single image. A video system does not merely have to create an appropriate image, it has to maintain consistency over time. Characters need to remain recognizable. Objects need to remain consistent, movement needs to make sense, and one frame needs to relate coherently to the next. This makes video generation a particularly demanding form of generative computation. Another important area is synthetic data. Synthetic data are artificially generated data designed to reproduce selected characteristics of real-world data. Why would an organization want artificial data? There are several possible reasons. Real data may be scarce. Collecting it may be expensive. Privacy requirements may restrict access to real records. Rare situations may not appear often enough in available data sets. Some situations may be dangerous, difficult, or impractical to reproduce in the real world. Or an AI system may simply require more examples for training or testing. In such situations, generative models can create artificial examples that help expand the available dataset. Potential applications include autonomous vehicle simulations, medical research, industrial testing, computer vision, and cybersecurity. Synthetic data therefore represents another form of generation. The model is not generating an article or an image for a human reader. It is generating data that can be used by another system or process. Generative AI can go even further into the scientific domain. Models can produce candidate molecules, proteins, chemical compounds, materials, and biological sequences. This does not mean that an AI-generated candidate automatically becomes a medicine, material, or scientific discovery. The generated structure is a possibility to be investigated. Laboratory testing and scientific validation remain essential, but the system can help researchers explore a much larger space of possible candidates than might otherwise be practical. This illustrates an important point. The value of generation depends on the context in which the output will be used. A generated marketing headline may require relatively simple human review. Generated software requires testing. A candidate scientific structure requires scientific validation. The consequence of the output determines the level of verification required. So far, we have discussed text, code, images, audio, video, data, and scientific structures as though they were separate worlds. Increasingly, they are not. Modern generative AI systems are becoming multimodal. Early generative applications often concentrated on one type of information. A text system worked with text. An image system generated images. An audio system worked with sound. Multimodal systems can work across several forms of information within the same interaction. A system might convert text into an image. It might examine an image and produce text describing or analyzing it. It might convert text into video. It may transform speech into text or text into speech. It may analyze a video and produce a written explanation. And it can increasingly work with combinations of documents, tables, charts, photographs, and written instructions together. Imagine, for example, that you provide an AI system with a business report. The report contains prose, financial tables, charts, and photographs. A multimodal system may be able to examine all of these forms of information together. It could then produce a written summary. It might create a presentation outline. It could prepare a spoken explanation, or it might help produce a visual output based on the information in the report. This is particularly important for professional work. Real-world information rarely arrives in one neat format. A business decision may depend on documents, spreadsheets, charts, emails, photographs, presentations, and conversations. A scientific analysis may combine written papers, numerical data, diagrams, and images. A training program may combine text, narration, illustrations, animation, and assessment material. Multimodality brings these different forms of information into a more integrated AI interaction. And that helps explain why generative AI is becoming much more than a writing tool. It is increasingly becoming a system for creating, transforming, interpreting, and connecting different forms of information. But this increasing capability also raises another question. If a model has to process text, documents, images, previous conversation, and generated output, how much information can it actually handle at one time? And why does a model sometimes appear to forget earlier information or produce a different answer to the same question? To understand that, we need to look inside the mechanics of language models more closely. In the next section, we turn to tokens, inference, context windows, and output variability. In the previous section, we saw that modern generative AI can work with many different forms of information, from text and software code to images, audio, video, and complex documents. But how does a language model actually process the information we give it? Why can a long document behave differently from a short prompt? Why does a model sometimes appear to forget something that was discussed earlier? And why can exactly the same question produce a different answer the next time we ask it? To understand these behaviors, we need to examine four closely connected ideas: tokens, inference, context windows, and probabilistic generation. Let us begin with tokens. When we communicate with an AI system, we normally think in words, sentences, paragraphs, and documents. The model does not process language in quite the same way. Before text is processed, it is divided into smaller units called tokens. A token is not necessarily the same as a word. A short, common word may be represented by a single token. A longer or less familiar word may be divided into several tokens. Punctuation, spaces, and other character combinations can also be represented within the tokenization system. Different languages may tokenize differently, and different AI models can use different tokenization systems. The important distinction is simple. Words are what people normally read. Tokens are the units the model processes. The process can be pictured as a sequence. Human readable language is supplied to the system. The text is tokenized. Those tokens are represented numerically. The model processes those numerical representations. It generates new tokens. And those generated tokens are converted back into the language that we read on the screen. Tokens matter at two very different stages in the life of a model: training and inference. Training is the process through which a model learns patterns from large quantities of data. Inference is what happens after the model has been trained, when someone actually uses it. Every time you ask a generative AI system a question, request a summary, or ask it to write something, the trained model is performing inference. For a language model, this happens iteratively. The prompt is converted into input tokens. The model processes those tokens and calculates probabilities for possible next tokens. One token is selected. That new token becomes part of the sequence. The model then calculates the probabilities again. Another token is selected, and the process continues until the response is complete. This explains something fundamental about generative AI. A language model does not normally retrieve a complete pre-written response from a database. It constructs the response as generation proceeds. Now consider what happens when the amount of information becomes very large. A model cannot process an unlimited quantity of information at the same time. Every model has a limit on the amount of tokenized information it can work with during a particular interaction. This limit is commonly called the context window. The context window can be thought of as the model's working information space for the current task. That working context may contain the user's prompt, previous conversation, documents supplied to the model, information retrieved from an external source, system instructions, and the response being generated. All of this information occupies context. Imagine, purely for illustration, that a model could work with a maximum of 100 tokens. If the input used only 20 tokens, much more room would remain for generated output. If the input already consumed 90 tokens, far less capacity would remain. Modern AI systems operate with vastly larger context windows than this simple example. Some can process very substantial documents and collections of information. But the underlying principle remains the same. Context is finite. This helps explain one of the behaviors that users sometimes describe by saying, "The AI has forgotten what I told it." The word forgotten can be misleading because it suggests human memory. A more precise explanation is that a model can work only with information that is available to it within the effective context of the current task. If a conversation becomes very long, or if large quantities of information are supplied, earlier material may no longer be available within that effective working context. So what appears to the user as "the model has forgotten something" may sometimes be better understood as "the information is no longer available within the model's current working context." This is why supplying important information again can sometimes improve performance. Another approach is to retrieve the relevant information from an external knowledge source when it is needed. Or a large body of information can be broken into more focused subsets for particular tasks. The same principle helps explain why long documents behave differently from short ones. A short question requires relatively few input tokens. A lengthy report may require tens of thousands of tokens. Several long reports may require far more. The longer the input, the greater the amount of the available context that it occupies. And because input and generated output can share the model's total context capacity, a very large input can also affect the amount of output that the system can generate. Document length is therefore not simply a question of the number of pages or words. For the model, it is also a token processing problem. There is another complication. Two documents with approximately the same number of words do not necessarily require exactly the same number of tokens. Tokenization can vary according to language, vocabulary, punctuation, character structure, and the tokenizer used by the model. So word count provides only an approximation of computational size. And longer input has another consequence. More tokens mean more information for the computing infrastructure to process. This brings us from context to output variability. Generative AI is probabilistic. At each generation step, the language model calculates probabilities for several possible next tokens. Suppose a sentence begins, "I took my dog." Several continuations may be plausible. "I took my dog for a walk." "I took my dog to the vet." "I took my dog with me." The model can assign different probabilities to these possible continuations. How the system selects among them depends partly on the model's generation settings and decoding method. One important setting is the maximum number of tokens that the model is permitted to generate. A lower limit restricts the length of the answer. A higher limit permits a longer response, subject to the system's overall limits. Another important setting is temperature. Temperature influences the degree of variation introduced when the model samples from possible next tokens. At lower temperature settings, the model generally favors the more probable choices more strongly. Output therefore tends to be more conservative and predictable. At higher temperatures, less probable alternatives have a greater chance of being selected. The response may become more varied or creative, but greater variability can also increase the possibility of poor or inaccurate output. Other settings control the range of tokens from which the system can choose. Top K restricts selection to a specified number of the highest probability candidates. If top K were set to 3, for example, the system would sample only from the 3 most probable possibilities. Top P, sometimes called nucleus sampling, works differently. Instead of specifying a fixed number of possible tokens, it selects from the most probable candidates until their combined probability reaches a defined threshold. Both methods influence how broad or narrow the pool of possible next tokens becomes. A random seed can make sampling experiments more repeatable. A repetition penalty can reduce the tendency to generate the same words or patterns repeatedly. And stop sequences can tell the system when generation should end. Most ordinary users do not need to manipulate every one of these settings, but understanding that they exist helps explain an important feature of generative AI. The model determines the underlying capability, but generation settings influence how that capability is expressed in a particular response. This also explains why the same prompt can produce different answers. If sampling is being used, some pseudo-randomness is deliberately involved in token selection. The first few words of 2 responses may be almost identical. Then one different token is selected. That token becomes part of the context for the next generation step. The next set of probabilities therefore changes. Another token may differ, and gradually the 2 responses can follow different paths. The same question may therefore produce different wording, different examples, different structures, different levels of creativity, and sometimes even different conclusions. This variability does not necessarily mean that the model is malfunctioning. It is partly a consequence of probabilistic generation, but it does have practical implications. For creative work, some variation may be desirable. If we are brainstorming ideas, writing alternative headlines, or exploring possible designs, variation can be useful. For factual, scientific, legal, technical, or other precision-oriented work, greater variability may be much less desirable. The appropriate settings therefore depend partly on the task. Finally, tokens also help us understand something that is often invisible to the user. Generative AI has an operating cost. Training a large model requires enormous amounts of computational work. Large models may be trained on billions or trillions of tokens, but computational cost does not end when training is complete. Every time someone uses the model, inference requires computation. The system must process the input tokens and generate the output tokens. The basic relationship is straightforward. Input tokens, computation, output tokens. A short question with a short answer requires relatively little processing. A long document requires more. A long response requires more. Multimodal information such as images, audio, or video can increase processing requirements, and more complex reasoning can also demand additional computation. So, organizations operating generative AI systems face a continuing balance among several factors: quality, speed, context, computing capacity, and cost. This is an important reminder. Generative AI may appear almost effortless when we type a sentence and receive an answer within seconds, but beneath that simple interaction lies physical computing infrastructure performing large numbers of calculations. Tokens, context windows, inference, and generation settings therefore explain much of what users experience when working with generative AI. They explain why long documents require different handling. They help explain why a system may appear to forget. They explain why identical prompts can produce different responses. And they help explain why the technology requires substantial computing resources. But understanding how generative AI operates is only part of the story. The more practical question is what all of this means when generative AI is put to work. Where does it create value? What kinds of professional activities can it support? And what happens when its impressive capabilities meet its equally important limitations? That is what we will examine in the next section. Generative AI at work. Its applications, benefits, limitations, and methods for improving reliability. In the previous section, we looked beneath the surface of generative AI. We examined tokens, inference, context windows, probabilistic generation, and the computing resources required to produce an output. We can now turn from how the technology works to a more practical question. Where does generative AI create value, and what should we understand about its limitations before relying on it? Generative AI can support work across a remarkably wide range of professional activities. It can help create content, analyze information, prepare first drafts, summarize documents, generate software code, support research, personalize communication, and assist with administrative tasks. The common feature is that the system can rapidly create or transform information that would otherwise require human time and effort. Consider marketing and communications. Generative AI can help prepare campaign material, website copy, social media content, advertisements, product descriptions, customer communications, and personalized messages. A human professional can define the objective, audience, tone, and constraints, while the system produces alternatives that can then be reviewed and refined. Customer service provides another example. A generative AI application may answer questions, summarize a customer's history, draft replies, explain products, suggest possible next actions, and personalize interactions. The benefit is not simply faster writing. The system can bring together information and generate a response that is relevant to the particular interaction. In software development, generative AI can support coding, testing, documentation, troubleshooting, and application modernization. It can help a developer move more quickly from a requirement to an initial implementation. But as we noted earlier, generated software still requires professional review, testing, security assessment, and validation before deployment. Research and knowledge work are another important area. Generative AI can assist with literature reviews, information synthesis, document comparison, question generation, hypothesis development, knowledge extraction, draft preparation, and presentation development. This can reduce the amount of routine intellectual production required before an expert begins the more demanding work of interpretation and judgment. Organizational administration also contains many tasks involving documents and structured information. Generative AI can assist with contracts, policies, job descriptions, meeting summaries, training material, procurement documents, invoices, and internal reports. In these settings, the technology can help convert information from one form into another and accelerate the preparation of routine knowledge products. Science, engineering, and healthcare extend these capabilities into more specialized environments. Applications can include synthetic medical images, molecular and protein generation, engineering simulation, scientific data interpretation, medical documentation, and research support. Here, however, the consequences of error can be much greater, so experimentation, clinical validation, scientific review, and regulatory requirements remain essential. These examples reveal several recurring benefits of generative AI. The first is productivity. Drafting, summarizing, coding, designing, and preparing routine material can often be accelerated. A task that begins with a blank page can instead begin with an AI-generated first version that a person evaluates and improves. The second benefit is lowering the barrier to sophisticated digital capabilities. Natural language interfaces allow people to ask for a summary, an analysis, a translation, an image, or a software prototype without first learning how to build an artificial intelligence model. The user can describe the objective in ordinary language and interact with the system directly. A third benefit is support for creativity and exploration. Generative systems can produce ideas, variations, alternative formulations, preliminary drafts, and design options. This allows users to explore a larger number of possibilities before deciding which direction deserves further development. Generative AI can also provide personalization at scale. The same underlying information can be adapted for different customers, audiences, languages, reading levels, industries, communication channels, or user preferences. Instead of producing one version for everyone, an organization can create many context-sensitive versions from the same underlying material. Another advantage is faster experimentation. A person or organization can generate several possible solutions, compare them, reject weaker alternatives, and refine the strongest ones. The technology can therefore reduce the cost of producing the first set of possibilities. Generative interfaces can also improve access to knowledge. Complex material can be summarized, translated, explained, or reorganized for different audiences. A long technical document can become an executive summary, a teaching explanation, a question and answer resource, or a presentation outline. But there is an important principle behind all of these benefits. The greatest value does not necessarily come from accepting the first AI-generated output unchanged. It often comes from combining machine speed and breadth with human context, expertise, judgment, and accountability. That is especially important because generative AI also has significant limitations. Perhaps the most widely discussed limitation is the hallucination problem. A generative model can produce information that is false, unsupported, or fabricated while expressing it in fluent and convincing language. The system is designed to generate a plausible output. It does not automatically establish that every statement it produces is true. This creates a dangerous possibility. Fluency can be mistaken for authority. A response may sound confident, contain sophisticated terminology, and be grammatically excellent, yet still contain factual errors. The quality of the language is therefore not evidence that the underlying information is correct. A second limitation is bias. Models learn from data, and bias can enter through training data, human feedback, fine-tuning data, retrieved information, system instructions, or even the user's prompt. Generated content may therefore reproduce unfair assumptions, stereotypes, exclusion, or discriminatory patterns present in the information or processes that shape the system. A third issue is inconsistency. As we saw in the previous section, generative AI is probabilistic. The same prompt can produce different answers on different occasions. Variation may be useful for brainstorming and creative work, but it can become a problem when a process requires strict consistency or repeatability. There is also the problem of limited explainability. With complex models, it can be difficult to determine precisely why a particular output was produced. This becomes especially important when AI is used to support decisions where the reasoning must be transparent, defensible, or auditable. Generative AI also raises intellectual property questions. Training data and generated material can involve issues of copyright, licensing, attribution, ownership, confidentiality, plagiarism, and commercial secrets. Organizations therefore need to consider not only what a model can produce, but also how the information entering and leaving the system may legally and commercially be used. Closely related are privacy and data security concerns. A user may unintentionally enter personal, confidential, regulated, or proprietary information into a generative AI application. Organizations therefore need clear rules governing what information may be supplied to these systems, where it may be processed, and how it may subsequently be stored or reused. Generative capability can also be deliberately misused. Convincing false text, images, voices, and videos can support misinformation, impersonation, fraud, reputation attacks, cybercrime, fabricated evidence, or misleading communication. Systems may also be exploited to generate phishing messages, malicious code, fraudulent identities, or other deceptive material. The applications themselves can face security risks. Prompt-based attacks or other forms of manipulation may attempt to make a system reveal information, ignore instructions, or behave in ways that were not intended. As generative AI becomes connected to more organizational information and systems, security becomes increasingly important. There are also practical limits involving resources and data quality. Large generative systems can require specialized processors, substantial computing infrastructure, technical expertise, energy, high-quality data, and continuous monitoring, and no amount of computing power can completely compensate for poor underlying information. A generative system is strongly influenced by the quality, diversity, currency, and representativeness of the data available to it. Poor or outdated information can contribute to unreliable, incomplete, or biased output. So can these weaknesses be overcome? They can be reduced, but they cannot simply be made to disappear. Several methods can improve the reliability of generative AI applications. One is fine-tuning, where a general model is further adapted using examples relevant to a particular task, industry, language, or style. This can make a broad model better suited to a more specific requirement. Another method is human feedback. People can evaluate model outputs and provide feedback that helps align system behavior with desired standards. Human review can also identify problems that automated evaluation may miss. A particularly important technique is Retrieval-Augmented Generation, commonly abbreviated as RAG. Instead of relying only on information learned during training, the application retrieves relevant information from external documents or databases and supplies that information to the model as part of its current context. Retrieval can provide more current information, incorporate organizational knowledge, improve factual grounding, reduce some hallucinations, and make supporting sources more visible. But RAG does not guarantee accuracy. The retrieved information may itself be incomplete, and the model can still misunderstand or incorrectly interpret what it receives. Another layer of protection comes from guardrails. These are rules and technical controls designed to restrict prohibited content, unsafe actions, inappropriate use of sensitive information, or responses that fall outside defined boundaries. Finally, there is human oversight. This becomes increasingly important as the consequences of an AI-generated output increase. Brainstorming ideas and preparing a preliminary draft require a different level of control from healthcare, legal work, finance, employment decisions, public policy, scientific research, or safety-critical engineering. This suggests a broader principle for working with generative AI. The question is not simply whether AI can perform a task. The more useful question is how the task should be divided between the capabilities of the machine and the responsibilities of the human. Generative AI can provide speed, scale, retrieval, synthesis, and generation. People provide context, domain expertise, judgment, ethical reasoning, verification, and accountability. Effective use often comes from designing the relationship between these two sets of capabilities. But generative AI is now moving one step further. So far, most of the systems we have discussed primarily create, transform, analyze, or explain information. Increasingly, AI systems can also use tools, access applications, maintain working information, plan a sequence of steps, and take actions in pursuit of an objective. That creates an important distinction between generative AI and another emerging category of systems. In the final section of this video, we will examine generative AI and AI agents and bring together the main lessons from our exploration of how generative AI works. In the previous section, we saw that generative AI can support many forms of professional work. We also saw that its usefulness depends on how its capabilities are combined with reliable information, appropriate controls, and human judgment. But the technology is now moving beyond systems that simply generate an answer or create a piece of content. This brings us to an important distinction between generative AI and AI agents. Most of the systems we have discussed so far primarily create or transform information. A user provides a prompt, document, image, or other input. The system processes that information and generates an output. The output might be a report, summary, image, software code, analysis, recommendation, or response to a question. An AI agent goes further. It may use a generative model, but it can also have access to goals, working information, tools, applications, retrieval systems, and workflows. Instead of simply producing an answer, the system can use these resources to pursue an objective through a sequence of steps. A simple example illustrates the difference. Suppose you ask a generative AI system to prepare a travel itinerary. It may suggest destinations, hotels, activities, and a possible schedule. The result is an output that you can read, evaluate, and use. An agentic system could potentially do more. It might research alternatives, compare available options, check a calendar, examine prices, organize possible choices, request your approval, and then use connected applications to carry out approved actions. The distinction can therefore be expressed quite simply. Generative AI produces an output. An AI agent uses information and tools to pursue an objective. This marks an important transition. Generative systems primarily create content or information. Agentic systems can increasingly interact with tools and applications and take actions. That additional capability also changes the nature of risk. If an AI system drafts an email and a person reviews it before sending, the human remains directly in control of the final action. If an AI agent is permitted to access an email system and send the message itself, the system has been given a higher level of autonomy. The same principle applies elsewhere. Generating a proposed purchase is different from placing an order. Preparing a suggested meeting schedule is different from changing someone's calendar. Recommending an action is different from executing it. As AI systems move from generation toward action, permissions, monitoring, approval points, security controls, and human oversight become increasingly important. This distinction between generation and action provides a useful point at which to bring together what we have learned throughout this video. We began with the relationship between foundation models and generative AI. A foundation model provides broad underlying intelligence that can support many different tasks. A generative model uses learned patterns to create new outputs, while generative capabilities describe what that model can do. Those capabilities become practically useful through applications. A generative AI application can combine the model with prompts, interfaces, data, retrieval systems, security controls, evaluation, guardrails, and human oversight. The application then uses those capabilities to support a particular user, task, workflow, or organizational objective. We also distinguished generative AI from many earlier forms of artificial intelligence. Traditional AI has often been used to classify, predict, detect, rank, or recommend. Generative AI uses prediction differently. It uses learned patterns and probabilistic generation to construct a new output. We then examined how this generation takes place. Models learn patterns and representations from large quantities of training data. When a user provides an input, the trained model uses what it has learned, together with the information available in the current context, to construct a response. For language models, this process takes place through tokens. The input is converted into tokens, the model calculates probabilities for possible next tokens, and generation proceeds iteratively until a response is completed. This explains why generative AI is not simply retrieving a fixed answer from a database. It also helps explain several behaviors that users encounter in practice. Context windows limit how much information a model can work with at one time. Long documents consume more of that available context. Earlier information may sometimes move outside the model's effective working context, creating the impression that the system has forgotten something. Because generation is probabilistic, the same prompt can also produce different answers. Settings and decoding methods influence how possible next tokens are selected, affecting the balance between consistency and variation. We also saw that generative AI is not limited to language. It can create and transform text, software code, images, audio, video, designs, synthetic data, and candidate scientific structures. Increasingly, multimodal systems can work across several of these forms of information within the same interaction. These capabilities create significant practical value. Generative AI can support drafting, summarization, translation, coding, research, design, personalization, experimentation, knowledge access, and many other forms of professional work. But capabilities should never be confused with reliability. Generative models can hallucinate. They can reproduce bias, generate inconsistent results, provide limited explanations for their outputs, and create privacy, intellectual property, misinformation, and security risks. Methods such as better prompting, fine-tuning, human feedback, retrieval-augmented generation, guardrails, evaluation, and human review can improve reliability. They cannot guarantee that every generated output will be correct. This leads to perhaps the most important conclusion from our exploration of generative AI. The value of the technology should not be judged only by what the model can generate. It depends on the entire system around the model. It depends on the context and information provided to it. It depends on the application through which its capabilities are used. It depends on the controls surrounding that application. And it depends on the quality of human judgment used to evaluate and act on its outputs. Generative AI is therefore best understood not simply as a machine that writes text or creates images. It is a probabilistic computational capability that can be incorporated into increasingly sophisticated applications and professional workflows. And as those systems evolve from generating information toward taking actions, the relationship between people and AI becomes even more important. That completes our first stage of understanding generative AI. We have examined what it is, how it works, what it can produce, why its outputs behave as they do, where it creates value, where its limitations lie, and how generative systems are beginning to evolve toward AI agents. The next question is no longer simply, what can generative AI do? The more practical question is, how should we use it? In the next video, we move from understanding the technology to using and deploying generative AI. We will examine how organizations identify suitable use cases, choose between different adoption approaches, select models and infrastructure, and evaluate whether a generative AI system is actually fit for the work it is expected to perform.